Recording. Okay. Any question before we start? Yes?
Yeah, for the lifting up level restorer, I have some difficulties on finding out the exact turn on or turn off status for the diode. Yeah.
Okay. Maybe let's do that after the lecture also. Any other question? General question? Okay. All right. So this part is kind of an overview. It is not included in your textbook. Don't worry too much about it. This is really more for your information only. And if you like to learn more about it, you can find this in EE 143. It is a laboratory course. Actually, you fabricate your own transistor. So that will be your souvenir to take with you if you take that course. So wafer fab, so the major advances in this field is so-called wafer fabrication. And we're going to go through some simple exercise, and you can see how powerful this technique is. On the picture here, you see two big wafers. These are silicon wafers, basically. This is silicon. And the current generation wafer is kind of looks tiny now. These are 300 millimeter diameter wafers. So that's roughly 12 inch, 1 foot. And that's still currently the main workhorse, the largest production using these 300 millimeter wafers. And the new generation on the horizon, so all the big players who can afford it are doing these 450 millimeter wafers. So this is 450 millimeter wafers. So you see that you need to be a really strong person to be able to carry even one wafer. And in production environment, these are all done by robotics. Robots pick up the wafer. So it doesn't rely on a human to load and unload the wafer or carry the wafer. But it's kind of interesting to put it in perspective, how big it has become. Even the weight has become pretty significant. And the industry is going in the direction where the size of the platform, so that's the wafer size, is growing bigger and bigger. At the same time, Moore's law says for the same area, we are packing more and more transistors onto the same area. And every transistor is getting smaller and smaller. So this is, as you all know, the general Moore's law. And making this transistor, I'm going to walk you through a process making just a p-n junction diode. So that's the simplest thing you can make is a p-n junction diode. And you can see how complex it is. And the real chip that goes into very low cost chips like those on your cell phones, it typically has repetitions of, we're going to see what is a photolithography process. So it goes through these steps about 60 times. Anything you do is 60 times is pretty complex. To build a fab, that is a factory, to manufacture these wafers, so it costs about $3 billion upwards for the 450 millimeter wafer, probably upwards of $5 billion to build a factory. And yet the cost for this wafer is amazingly cheap. For example, for the workhorse now, many of the chips actually are still made in 200 millimeter wafers or 8-inch diameter wafers. 8-inch diameter wafers, $1,000. You can buy a fully processed 8-inch wafers. So that includes you do this process 60 times. It's pretty complex. And yet it cost design house about $1,000. How many things you can buy for $1,000? You can buy. What if you have $1,000? What would you buy? A laptop. Half of a laptop. Half of a decent laptop. A phone, iPhone 10. That's $1,000. Anything else? If you buy a car, that's more like tens of thousands of dollars. And yet the complexity going into making one of these wafers is actually almost higher than that of making a car. But it costs $1,000. Many of your chips, if you look at your cell phone, of course, the processor is very big, bigger than a centimeter by a centimeter. Many of the smaller chips that do a lot of things are on the order of millimeter by millimeter. So let's do an exercise. On a 200 millimeter wafer, if you have a calculator, divided $1,000 by just the area, square millimeter. Anybody have a calculator? Nobody has a calculator. I have one. So it is, anybody has done that? About point 0.013 dollar per millimeter. So 1 penny per millimeter square. That's incredibly cheap. Of course, if you buy just 1 millimeter, it's the same cost. You have to pay $1,000 to get your millimeter. But everybody pool together. Everybody buy the same thing, so you divided the cost. And of course, if you just want to make one wafer, your cost will be significantly higher. The reason it costs only $1,000 is because you order something like tens of thousands of wafers per month. That's what gets you to this low cost. So everything in all the equipment, all the manufacturing costs has been amortized over the entire large number. So it's really economy of scale. You really need large volume to drive down the scale. So if you go to the most advanced wafers you can buy now, 300 millimeter wafer, well, the transistors are more advanced. The speed is faster. And you can buy more transistors per millimeter square. The wafer is going to be more expensive. How much more? 10 times more. That's a lot more. 10 times more. Well, again, if you look at small areas per millimeter, it is about, I think, about $0.14 per millimeter square. So for this reason, we say basically chip costs nothing. Everything else is what's surrounding the chip. The design cost, the cost of human designers, packaging, the cost of putting them into a package. That turns out to be more than the cost. The overhead is about 90% of the cost. The chip itself, despite the complexity, really costs nothing unless you're making some really special chips. So what goes in there? Okay. It's a repetition of this following process here. So you start with this wafer. This is the 200 millimeter or 300 millimeter. So this is the silicon wafer that you started with. Okay, and you repeat the following steps. One is deposition. You add materials. So you add materials. Okay. Add material, this step is typically called deposition, okay? And for silicon, if you recall in the first lecture, we say silicon became the dominant material in the early days, in the 60s, because it has very stable oxide, silicon dioxide. So this silicon dioxide, you can simply grow the oxide by putting the wafer at high temperature together with oxygen, or with water vapor. You basically put it in the steam, and at very high temperature, like 1,000 degrees C, the silicon starts to oxidize. And then when they oxidize, they grow very high quality silicon dioxide, which becomes the insulator. That's the first 4 decades of transistors, all relying on the very high quality silicon dioxide. And then you do the second distinctive step called patterning, or commonly known as a lithography, okay? And some of you who have done our work, you've done lithography. It's very similar process. It's basically a printing process. A lithography, you take a master, okay? The master has certain patterns you already design on it. This master is usually called a photomask, okay? And photomask, in the simplest case, looks like a glass with patterns that are opaque and with some openings that you will let light through. It's kind of like a screen printing screen, okay? And this allows you to do a photo exposure process. It's kind of like photography process. You expose this photosensitive layer called photoresist. Photoresist is a photosensitive, okay? Photosensitive, it's a chemical. Once exposed to UV, it changes the chemical property of the area. So the high energy UV photons activate some chemical reactions. So this part of the resist is generally organic resist. It becomes, say, polymerized. So this part becomes kind of a hardened layer. And after this exposure, you will bake it and put it in a chemical solution. So after development, if you, this is a lost art now. If you are interested in traditional photography, you take a negative after exposure. You take the negative in the red room where it's not sensitive to additional light. You put it in a chemical, wash it, and the pattern that's being exposed will come out. So it's like a hard imprint onto your negatives. This is very similar to that process, and the chemicals are slightly different. But once you develop the chemical, you now have a pattern, and the pattern you can take it to a process. You remove the material, okay? So you remove the material. This process is generally called etching, okay? You etch the material away, okay? In this case, we etch silicon dioxide away. So this is one full cycle of a unit process. You put on some material, you deposit, you produce a pattern, you remove part of the area of that material, so you do etching, okay? Then you build on top of that, you do the next step process. So let's stop for a moment talking about this exposure process. Yes, question?
On the last slide,
yeah.
it's called PSI, is that the positive type?
Yes, so this is a P-doped silicon. It's kind of common to start with P-doped silicon, okay? And this is same as a p-n junction P, all right? So this lithography process, this process is done basically in a gigantic camera. So this gigantic camera has a simple system. Basically, it's really like your camera. There's a lens, okay? So here is a lens. And here is your wafer, right? And you have this photosensitive material, you coat it on it. So this is called photoresist, okay? Photoresist is kind of like the negatives. And then the pattern is usually spatially apart. So this is the photomask, that some part of it is opaque, some part of it is transparent. So this is a photomask. And there is usually a light source, so like a lamp in the traditional case. So here is a UV lamp, okay? So it basically illuminates this photomask, and then this lens perform imaging, okay? And the same mask got produced here, usually over a small area, and then you move the wafer to expose to the next area. So this is called expose. Okay, you expose, and then step. Step means you move to the next area. So this lithography machine, this expensive camera, is called a stepper. Step and repeat. So short name is called a stepper. Stepper, think of it as an expensive camera, okay? And wafer basically lives inside the camera, just like negatives, okay? Now, you all hear about this Moore's law, and we keep making smaller and smaller features. So what enables us to make smaller and smaller features? Well, basically, we learn how to build better and better cameras. This camera has higher and higher resolution. Back in the 80s, we make feature size on the order of 1 micrometer. 90s, we make 0.1 micrometer or 100 nanometer. And now we make on the order of 10 nanometer. So it's really coming down exponentially. Now, we are running into a fundamental limit. For those of you who are these old-fashioned amateur photographer, there is a resolution limit that's kind of independent of technology. That's called diffraction limit. So light is an electromagnetic wave. Ultimately, you run into a limit on the resolution here. The resolution is limited by diffraction, okay? Diffraction limit says the smallest feature you make is on the order of wavelengths. Let's say roughly wavelengths divided by 2. Okay. Wavelengths, lambda is wavelengths, okay? Lambda here is wavelengths. So we start to go to shorter and shorter wavelengths. Visible, well, we typically start with UV. UV, 300 nanometer. We start with 300 nanometer. We go to 254. We go to 193. So right now, lambda is at UV wavelengths, 193 nanometer. Okay. Now, these wavelengths available source is not a continuum. It depends on what's available making this a good source. So 193 nanometer, it actually comes from a UV laser. It's no longer a lamp. It is a UV laser. It's a serious laser now. And the next laser is you need to search for it and you need to develop it. It's usually a very expensive process. Wavelength is not getting any smaller. How do we make structures smaller than a wavelength? Well, that's how this industry have developed. They actually make structures smaller than a wavelength. The second latest thing is they start to immerse the whole thing in water. So you start to put the whole thing here in water. Water is known to have a refractive index of 1.3. Okay, so the refractive index is 1.3. Refractive index will appear in the denominator of the resolution. So you get an instant boost of 30% performance improvement by doing, if you hear this name, immersion lithography. Okay, immersion lithography. Basically, you immerse the whole wafer in water. If you have seen the machine, you will appreciate the complexity. Usually we keep the wafer dry. Anytime you touch its water, it's pretty, it's a cumbersome process to even dry it. So to immerse the whole thing in water is a big deal. But this is what keeps Moore's law going for the past 10 years or so. We are running out of juice of this technology. So the next thing on the horizon, not yet in your cell phone, but probably will be in within 3 to 5 years. This is called EUV. The machine is shown here. EUV stands for extreme violet, ultraviolet. It is actually way below UV wavelengths. UV wavelengths, you think about wavelengths on the order of 100 nanometer. The visible spectrum goes from 350 nanometer to about 750 nanometer. Depends on your sensitivity of your eyes. Some people can see a little bit redder than other people. On the short side, 400 nanometer probably is the cutoff, beyond which is UV. So 193 is UV. This EUV is really X-ray. This EUV is really X-ray, what we call soft X-ray. Now, X-ray, raise a lot of alarms, right? X-ray is radiation, scares people away. So industry figure out, well, if they call it EUV rather than X-ray, it's easier to gain acceptance. The wavelength is 13 nanometer. So that's really an order of magnitude shorter than UV. It is really an X-ray. And X-ray, what generates X-ray? Well, it's kind of almost like a tabletop accelerator that generates X-ray. So it took the industry many, many years to develop a robust, reliable light source. And they are on the verge of doing that. So the machines are available in all the advanced foundries. They all have these prototype machines. The machine looks, okay, let me see, just went to sleep. Okay. Okay. Don't want to download. All right. Okay, we are back. All right. So this machine is gigantic. So you see this person in front of this machine. It is a very complex machine. The wafer actually is constantly moving. So it's somewhere a huge distance away. If you trace the system, there is this soft X-ray laser, and it's shooting out beams that you no longer use lens to do imaging. Lenses are no good at this wavelength. It is really very exotic optical materials. Usually it's a reflector because transmission lens is not good anymore. So these are the optics, and even so-called the master, the photo masks has become very, very complicated. And you need all kinds of complex optics to make it work. That's how it becomes kind of this gigantic scale. And the reason I have this picture of the 787 here, Boeing airplane. Anybody own private jets? Anybody know how much it costs? You do? How much does it cost to buy a jet like this?
Depends on the jet. It's like around 5 million above. It depends on the jet.
Depends on the jets. So 787, Boeing 787, Dreamliner. 200 what, million? Yeah. Maybe with the volume discount. So roughly 300 million. You can own your jet. If you want to make your own wafer, this costs about 100 million per model, okay? And maintenance cost typically is more than 10% every year. So it's not a trivial matter now for anybody to say they want to build a new fab. This is the commitment. That's why a new fab costs, $5 billion. Because it has a couple of these machines. You need to keep it running all the time. Nothing can go down, right? So it starts to become very expensive. But this allows continuous scaling of the Moore's law. So now with this, people are talking about going down to maybe so-called the next node. People talk about 7 nanometer node. and the next one 5 nanometer node, and the next one 3 nanometer node. Okay, for next 10, maybe 20 years. Now every generation will have to be longer. If you buy such an expensive machine, you got to use it for a long time before you buy your next machine, right? If you own an airplane, you better carry a lot of passengers before you have enough revenue to buy your next airplane. Right now, the 193 nanometer lithography is about 20 nanometer node, 16 nanometer node. So this allows the revolution to continue. Okay, now back to our simple fabrication flow. Once you've done that print, that lithography, that expensive photography process, now you have a pattern. So we have the silicon dioxide pattern here. You need to do something with it. Let's say we are making a p-n junction diode. The substrate is p-doped, so we need to introduce n-type doping. N-type doping is available through dopant like arsenic, like phosphorus. Okay, so what you do is you ionize these impurities, and then once it becomes ionized, it carries charge. With a charge, you can accelerate the charge. So you put into an ion implanter where basically you think of it, you produce these arsenic ions, and you put accelerator here, minus, plus. So you shoot out these impurity at very high energy. How high energy? Well, you shoot it into this wafer here. You shoot it with energy, typically ranges from tens of kilo electron volt to very high energy one that it reaches, 100 kilo electron volt. Some unique processes sometimes use 1 million electron volt, 1 mega electron volt, if you want to go really deep. So this is like shooting a bullet through a pile of woods. There is a so-called stopping distance. And this sounds like a very chaotic process. You're shooting a bullet, and the bullet will stop when the friction and all these random process eventually dissipate all your kinetic energy, and the bullet will stop. And yet, it is one of the most reproducible process in the silicon processing. And the depth, so you will have a distribution of your n-type dopant, and the distribution usually is very well behaved, very well characterized. It has a Gaussian profile. There's a mean distance. There's a deviation, standard deviation. These are all very well characterized. So depends on the type of p-n junction you want to design. So you control the dopant. You control how much arsenic you put in, the so-called dosage. You control the depth by controlling the ion energy. So you can have that all to your disposal. The next, you need to make electrical contact. So you need a metal. Ultimately, current goes through metal. So for metal in the early days is aluminum. That's constantly used. So you put aluminum everywhere. That's another deposition process. It's a process you basically put aluminum clusters of atoms until they cover the full wafer. And then you need to pattern your metals, okay? So you go through another lithography process here. You have resist here again. You coat it with resist. You expose it, and then you etch the area that's outside the exposure area. So you pattern your metal now. So you pattern your metal, okay? So I mentioned each of these processes is a photolithography process, usually associated with depositing some material and etching some materials. How many lithography processes have we gone through now? If you recall the process we just walked through, how many times have we done that? 2. In this process, 2, right? So in CMOS, you've done that 60 times. So that's just illustrate the complexity. And usually you get your chip, there are some kind of passivating materials. Silicon nitride is used here. In the simplest process, that's it. If you buy discrete p-n junction diode, then you dice it up. That's the p-n junction diode you get. For example, the photodiode in your lab 3, basically this is the process. You have a photodiode. This p-n junction is sensitive to visible light for silicon. You have a p-n junction diode. You need a bottom contact, so you need the metal here. This example says gold. Gold is actually a forbidden material in the fab. Gold causes defects, deep level defects. So if a lab is contaminated with any tiny traces of gold, the whole fab shut down. Everything that goes in there, there's a very sensitive protocol, very complex protocol to make sure gold never gets in there. Usually, you have aluminum or other process, other metal that are more friendly. So here, when you see your photodiode, it looks like you have 2 leads coming out, right? So this go to the package. Here is 1 lead eventually. That lead connect to this wire, and another lead eventually connect to the substrate. And you can apply voltage, and your p-n junction is actually on a subset of the areas inside the chip, depends on how large you pattern that. So this is a p-n junction, okay? So now you know how all these complex circuits are made. You've done that just repeating many, many times. And the process, so this starts to look like what you might have in your pocket. This is Intel 14 nanometer, one of their advanced microprocessor chip. Intel still are the leader in terms of this technology. And what you see here, all the process we talked about is actually invisible here. Here is a transistor. The transistor is here, okay? We're going to talk about transistor next. These are MOS transistors here. It's not, you cannot see it under this magnification. What you see instead are these metal interconnect layers. So there are many, many layers of metal interconnect. These metal interconnect build your circuits. In your lab, you have breadboard, you have wires, you connect from one component to the other. In the circuits, they are all building, they are all printed, and you need many, many layers in order to do the routing. So in this case, 13 layers. 13 layers is kind of typical for circuits like microprocessor. You need 13 layers of metal to route it. You see this layer is very, very thick, right? And towards the bottom, they are very, very thin. So different metal have different functions. These metal here, they carry power. So usually these are power and ground, okay? Power or ground, they are very bulky. A lot of current flows through these layers. You need really low conductivity. And conductivity is better. If you make them thicker, they carry more current. Towards the bottom here, they are contacting individual transistors. So each transistor actually consumes tiny amount of current, and the metal can be skinny here. And you need to be same size as the transistor in order to wire individual transistors. Okay. All right, that's pretty much it. Question?
What are those little rectangles you're seeing that are connected to anything below it?
These rectangles?
On the top right?
These are wires. So this is a cross section in scanning electron microscope. So imagine these will be the wires. So these are wires running in this direction. And there are many rectangles here. These are also wires running in the longitudinal direction. And it looks very regular here, so it almost looks too regular to be a wire. So sometimes in order to ensure the uniformity of the process, they put dummy squares there. Even though you don't have any metal interconnect there, they put metals there for nothing, so that when they do the etching, they always see the similar fraction of metal areas.
Why don't they make the metal area smaller?
Which area smaller?
With the wires and the metal in the metal interconnections, we're able to make transistor that's tiny, that
Right.
is not visible. But
Right.
why don't we make them?
Why don't we make wires also very small? So wires, as you know, have resistance. Resistance is equal to your resistivity times really your length and your cross-sectional area. Length is kind of fixed by your circuit. You need to go from here to here. So cross-sectional area is the one that you control your resistance. And usually when you have a transistor, we're going to talk about circuit. So you have a transistor that looks something like this. It's going to drive the next stage transistor here, okay? And transistor, as you learned in 16, this looks like a capacitor here, okay? But this wire is really a resistor. It's not a perfect conductor. So you have R here and you have C here. And while you're trying to charging the capacitor, you dissipate power. And majority of the power dissipated in integrated circuits, like 80–90%, are basically dissipated in charging capacitor, which means you lose power to the parasitic resistance here. And so it's very important to keep it as low as possible. And that explains why in the early days, these are all aluminum. And in modern day, guess what this metal is? What has higher conductivity? Copper, yes. So a lot of them are copper. Gold has better conductivity, but we say no gold. Gold kills everything. In between gold and copper, there's another metal, silver. Why not silver? Expensive, yeah. Silver is actually not that expensive. It's more expensive than copper, that's true. Silver also oxidizes easily, so it's much harder to process silver. Okay. Any other question? Yep.
In ion implantation process,
Yeah.
the positive ion is shooted to the wafer.
Yeah.
The wafer still charge neutral.
That's a very good question. Yes. So you imagine you keep shooting ions in there. So this needs to be grounded. So this implanter, this machine called implanter itself is a circuit, and you need to have a closed loop. Otherwise, you build up so much charge, your next ion will go into deflect, and that's a problem. So you need to conduct it usually through substrate. Yes?
On the last slide of the process where you were removing the silicon nitride,
Yeah.
how would you remove that silicon nitride?
So all the process that, for example, you pattern the metal, or you pattern the silicon dioxide, or you pattern silicon nitride, these are all done by processes so-called dry etching now. Dry etching use chemical ions in a state called plasma. The only natural occurrence you can think about it in the polar region, you see northern light. There are lots of ions being accelerated. You see it glowing. Helium, they are neon lamp. Those are they are plasmas inside, so glow discharge. And so you energize the ions, different ions for different materials, and then you accelerate them towards your opening. You cover everything by photoresist. So the ions can only attack this area, and you make an opening. So companies around here, like Applied Materials, they are a dominant supplier. Actually, both companies, Applied Materials and Lam Research, these are two dominant suppliers for this type of equipment. For the lithography machine, all the dominant players are overseas. ASML is from Netherlands. Yeah.
For like metal deposition, chips that have tiny feature size.
Yeah.
How is that metal deposition?
This process, like what we drawn here, is a highly simplified. Now, if you go to the 10 nanometer transistors, somewhere the metal has to be very small. So if you have one layer of metal here, and you need to make a connection to it, so you'll put intermetal dielectric, okay? So something, think of it like a silicon dioxide. So you make a tiny hole, three-dimensional, this is a tiny hole, and you deposit a particular type of metal that can go into the tiny holes. So tungsten is often used to fill those holes. Tungsten, so these are called tungsten plug. It literally looks like a tiny plug, and they fill the plug, and then after the plug is filled, you put another level of metal, and this metal will be copper, and copper will contact through the bottom layer copper through this tungsten plug here. And so it's decades of experience on choosing what materials, how to deposit, so they are very uniform, conformal when it goes to tiny holes. Okay. All right. Okay. For those of you who are interested enough to do this hands-on, so EE 143 is the course that if you really want to make your best value of your education, the department spends way more money than they still charge you a lab fee, but the actual money that costs the department is way more than what they charge you. Okay.